end of 1999, the first time that I met him. And then when I started my PhD program, he was on my committee. It was a great experience to being taught by a great scientist and to be able really to do that, what you see here, the Middle East pollutant transport boundary transport, and to do that for the countries that are not really working together as well as we should have. And let's see, the idea over here was really to find a way how to make the connection between scientists in the West Bank, Gaza, Lebanon, Jordan, and Israel. And that was a great initiative that Bob was heading. He's the PI of that program. That took for many years. It had few phases, like 3 phases over here, as you see, that really takes for account the science of because pollution doesn't have boundaries. It moves from one place to another, and because of the wind. So you can't make a decision of how you are looking at that part. But if you want to collaborate between different people, then this is what we were. Bob really made up, and he was able to connect. For me, at least, I was heading when I finished my PhD program and I became a postdoc at Bob laboratory. I was heading a Palestinian student called Kasashe that he was doing his master's degree over there. So there were like 4 Palestinian students that were working at San Jose State and DRI and got their degrees, and 2 Israeli that finished their PhDs, and one of them is myself. And at that research effort, what we were doing was really to figure out the photochemical understanding of what is happening in Israel, especially to the ozone peak. In order to do that, we had to build first the first emission inventory for Israel, spatial inventory, understanding who is contributing more. Is it the stacks or the vehicles or vegetation? Who's responsible for the ozone peak that is happening? Doing the RAMS model. I know that most of you are WRF people or MM5 or MMX, but still my advisor at that PhD is Isaac Marr, also who passed away, that wrote RAMS, and I had to give him also the honor of heading the meteorological part. So you can see here again the agreement between observations that you see on the left side, on the right side. This is the RAMS model that is working, and this is the emission inventory that I was talking about. Building that emission inventory took me for almost 2 years, understanding that what you see is not always what is the reality. So if you're gathering a lot of data that comes from the government, it's not especially what you get. So be careful when you are building out your own database. You need really to qualify it and to validate that in order that you will be able to do your own modeling that would work as well as you would hope that it would. So over here, what you see is like the model that I ran was Canex. It's close by, a close cousin for the WRF-Chem, and running that for Israel in those 3 nested grids, running it for the area, and finding correlation, a good correlation that what you see here on the right side, that red dot is on that line, the continuous dark line that you see here is a plane that is running on a height of 300 meters inside the boundary layer, and finding that peak over Jerusalem that consisted and happened in many ozone events. And we found that you could represent it and find it again over here with the model. But the model was showing a very big peak over Jordan that nobody was measuring. And because of the model, we were doing that is like to quantify who's responsible. Is it the stacks or the vehicles. And it was discovered that for Jerusalem peak, it was the vehicles, and for the stacks, it was because of the in Irbid, in Jordan, it was because of the stacks. For the vehicles, it's over Jerusalem. So we were doing an observation phase, and phase two, that we went throughout and found out that the area in Jordan that is called Irbid really went and got that from observations, doing mobile stations that went to Jordan and finding out that we had those situation of high ozone peak again because of model. So the model is able really to quantify and find things. So the application part, and that would be like the next phase of my life as a scientist, going into the applicative world and doing a company, a nice company, that relies on the understanding that what is important is, first of all, the measurements that you could use in order to validate models. And of course, down the road, hopefully, if hyper-local data is out there, to assimilate that and put that into the use of our high-resolution models like the NVMe that you're working very hard. So the main idea is really to use sensors that are already out there inside digital appliances, and mostly the one that you're now playing with. I'm sure like most of you have that in your pocket or in your hands. I see out there at the back. It's the most the greatest way that you should hold the phone. It's like doing a WhatsApp or reading something. Then it is able really to do the measurement at the background, and this is what I'm showing over here. It's like we are collaborating with Qualcomm and ST, companies who have the sensors and also the motherboards for the phones, that it would be done at the background. You don't need to open an application. It will do a measurement, a qualified measurement. If you want, it will be opt-in into the database. If not, then it would not. What I'm showing here is like a regular Xiaomi 11 that, as you see, somebody was disturbing the air quality over there with a deodorant. And what you see in the gauge that goes from green to red, those are the EPA air quality index levels, and that you are able now to see that those particles that were distributed in the air descending down, and then the amount of concentration that are in that room at that time is getting lower and lower. So that's the part about using the hardware that is already out there. The idea is also that it would be able to detect smoke as a smoke detector for your end user. What you see here is not the camera that is capturing that. It's again the LiDAR. As you see here on this side, this is the LiDAR. It's very, very small. It's a laser and a radar, of course. You have that in most of the high-end smartphones as the autofocus system that is working. And with that, we are able really to measure and quantify the amount of particles in the area. So the idea is really to have a software that would be embedded inside the phone, manipulating and using the sensors like the LiDAR, like the microphone and speaker in order to detect temperature and also to do relative humidity. You are also able to detect, as I told you about the phone, what is the context of it. If it's in your pocket, in your hand, is it on a surface? By that to really validate that this is a good measurement that can be used to this kind of parameters that are nice, like temperature, relative humidity, noise, UV, understanding if the phone is indoor or outdoor. Again, to validate a system that if we want to do a modeling for the outdoors, you really want to rely on a system that tells you that that measurement was done outdoors and not indoors. And of course, the indoor data is very important, and I think this is really what is governing our well-being and health, dependent on what we are breathing and what we are exposed to. Because most of the time we're indoor and not in the outdoors. So that is also important. So the platform that we have already is gathering all the data that comes from the the satellites, from public stations, governmental stations. We are also employing cars that we add a mounted station to the top of the car in order to have a cross correlation between the phones and also that data that comes from the cars, in order that those phones are not um, being controlled by technicians, but the systems that we deploy in a city, like 10 or 15 stations, mounted mobile stations, are being controlled by technicians, by our technicians, in order that they will be validated and qualified, so we can really do the thing of qualification, aggregation, and unification of the data in that data lake that we have here, and then use that for the modeling. If we want to do, of course, an ensemble or random wharf cam, and then do a lot of machine learning in order to clean it up, that it would look better and it would be more accurate for our customers and your customers again. And I see you as the scientific community as a customer, of course, for that kind of database that you could use for validating the models and for initial and boundary conditions for those models. So that's the resolution that we are getting without the cars, like 100-meter hexagons running a wharf cam. What you see here is a platform that is already running with the cars inside in Jerusalem. There are 6 mounted taxis with the stations, and that you could see that is the resolution is much smaller than 100 meters. Every 10 seconds there is a measurement that you can rely on and use that in order to qualify different decisions making by the planners or the scientific community again. I'd like to explain more about that. And I think that everything that I show here is started from the beginning because of Bob, that his idea of the measurement and modeling have to go hand in hand. You can't do something without observation, or the observation without the modeling. Because with the modeling, we were able to find new observations, and because of the observations, we are able to validate and make our modeling good enough and even better. So I think that to conclude that, thank you very much. Bob, you have a last presentation in a second.
Thank you. All right. Well, Erez, I know now where this background is coming from, all right? From here. Well, we've been using that for a long time. As you recall in this case. So thank you very much. I assume that Bob has some stocks in your company, no?
Of course.
Yeah. Very